Hello, welcome to session 6 of data communication. Today we'll be looking at data link control, a very vital part of data communication. Now, for an effective data communication, much more is needed to control and manage the exchange of data. Now, to control the sending of data over a link, a layer of logic is added above the physical interfacing, physical layer. And this logic is referred to as the data link control or the data link control protocol. Now, when a data link control protocol is used, the transmission medium between the system is referred to as the data link. Now, what is flow control? Now, flow control has to do with the sending station not to send frames at a rate faster than the receiving station can absorb. In other words, the sending station shouldn't overwhelm the receiving station with data. So we need to find ways and means to be able to control the amount of data that comes to the receiving station from the sending station. Error control has to do with the bit errors introduced by the transmission system, and these has to be corrected. Then of course we have addressing. Now, on a multi-point line such as the local area network, the identity of the two stations involved in a transmission must be specified. So if sender A is the one doing the transmission, we should be able to identify that this is sender A, and we do that using the IP addressing. So we will know that either this is coming from a .10 or a .2 or a .3. So basically, that's what we have been discussing, that a flow control is a technique for ensuring that a transmitter or a transmitting entity doesn't overwhelm a receiving entity with data. Now, in the absence of the flow control, the buffer in the receiver may fill up or may be used as a way of controlling data. Now, the first type of flow control we want to look at is the stop and wait flow control. Now, the simplest form of flow control that we have is this stop and wait. And the source, here the source transmits frames and it gets to the destination, but the destination needs to reply with an acknowledgement, or an ACK message needs to be sent before any other frame is being forwarded. Now, the destination can decide to stop the flow of data by just sending or by just withholding this acknowledgement. So once the destination withholds this acknowledgement, it gives an indication to the sender that no communication is required anymore. Now, large blocks of data may be split into smaller frames or fragments. Why? Because we have limited buffer size. Then errors are detected also sooner once the frames are in smaller sizes. Now, when there is error, retransmission of the smaller frames is needed, and it's even faster, and this prevents one station occupying the medium for a long period of time. The next flow control has to do with sliding window, and sliding window allow multiple frames. Unlike the stop and wait, sliding window allow multiple frames to be transmitted between the sender and the receiver, and to keep track of which frame has been sent or which frames have been acknowledged. Now, each frame is labeled with a sequence number. So we have 1, 2, 3 being labeled to the frames. Now, the receiver acknowledges a frame by sending an acknowledgement which includes the sequence number of the next frame that it is expecting. So in general, for a k-bit field, the range of sequence numbers is from 0 through to 2 raised to the power k minus 1. For instance, if I have a 2-bit field, it means I'm having 0 through to 3, because I'll have 2 raised to the power 2, which is 4, minus 1 frames. So I'll have from 0 through to 3. In effect, it still makes it 4 anyway. Now, frames are numbered with modulos, or using a modulo symbol. So, mod 2K. And that's how the frames are numbered. Error detection. How do we detect error? Now, for a given frame of bits, additional bits that constitute an error detection code are being added by the transmitter. So, once you are sending a frame, bear in mind that another bit or another frame is being added, and this is what we are calling the error detecting code. This is added to the transmitter, or is added by the transmitter, and this code is calculated as a function of the other transmitted bits. The receiver performs the same calculation and then compares both values, what is received and what is in the transmitter, and compares these two values. So this is a block diagram of how to detect error. We have a k bits of data, and like I said, it's a function of the data. So we have E being the function of f of data. Now, once that is performed, we have the bit that is being added, the small bit that is being added, which is the n minus k bits. That's added to the data, and that forms part of the n bits. Now, this is being transmitted and it comes to the receiver. Now, once the receiver gets the bit stream, what it does is that it already has a complement of this function. So it compares that to the bits, the error detecting code. And once it is the same, it means the data received is correct. Once it's different, it means the data received has some bit of error. So we have the E and the E prime, which are the error detecting codes. Then we have the F, which is the error detecting code function. So the simplest error detection scheme is to append a parity bit to the end of the block of data, which I've explained earlier on. Now, even parity is used for synchronous transmission, and odd parity is used for asynchronous transmission. Now, the most common and most powerful error detecting codes that we have is the cyclic redundancy check, which we call the CRC. Now, given a k-bit block of bits or message, the transmitter generates an n minus k bits sequence known as a frame check sequence, FCS. So hence the total number of frames to be transmitted is n bits, and this can be divided by a predetermined number. Now, there are 3 procedures with regards to CRC. We have modulus 2 arithmetic, we have the polynomials, and we have the digital logic. Now, you need to refer to William Starling's book to find out how to calculate the various procedures of the CRC. Now, I want to look at error control. Now, error control refers to the mechanism that detects and corrects errors. Now, these errors occur in our transmission of frames. Now, there are 2 possible types of errors that we need to control. First is the lost frame. So, in the course of transmitting a frame over the transmitting media, the frame gets lost. Another one we want to look at is the damaged frame. Yes, you've transmitted a frame, it's on the transmission media, but something happens to it and it gets damaged. It gets spoiled. So these are the 2 types of errors we'll be looking at. Now, these errors can be controlled by one or all of these mechanisms. We have the error detection, which we've just explained. We have a positive acknowledgement. We said that once the sender sends the frame, the receiver needs to acknowledge that that's received that frame, and that's what we are terming the positive acknowledgement, the ACK. Then we have retransmission after timeout. Anytime the frame gets timed out, there needs to be a retransmission. And of course, we have negative acknowledgement and transmission. Now, all these collectively is known as the ACK, or the automatic repeat request. The ACK, the automatic repeat request. Now, there are three forms of the ACK. We'll be looking at the stop and wait ACK. We'll look at the go back end ACK. Then we'll look at the selective reject ACK. With all these, we'll look at the various types of error with regards to the lost frames and the damaged frames. So we'll look at the stop and wait ACK. And this is based on the stop and wait flow control, which we talked about earlier on. The source station transmits a single frame, then waits for an acknowledgement. Now, if the received frame is damaged, then it's discarded, and transmitter always has timers which expires. So if no acknowledgement within the timeout session, then a retransmission needs to be done. Now, if the ACK is damaged, then the retransmitter or the transmitter will not recognize this. Why? Because the transmitter will now have to retransmit the frame. Then the receiver gets, what happens that once the acknowledged frame is damaged, of course the receiver will not acknowledge or will not recognize that frame. So it means that the transmitter will have to retransmit. Once it does that, it means 2 copies of the frame has been sent. So it has to find a way of indicating that this is to acknowledge the first and this is to acknowledge the second. So here with the stop and wait, we use 2 acknowledgements, ACK0 and ACK1. Now the advantage here is that this is simple. It's its simplicity for stop and wait, and its principal disadvantage is that it's an inefficient mechanism. Now, the use of sliding window is used to improve this efficiency, which we are calling the continuous ACK. Now, go back end ACK, and this error is based on the sliding window flow control. If no error, then the destination acknowledges frame with an ACK. And here the ACK is of the type RR, or receive ready. It means that it's ready to take up the next frame. It uses windows to control the number of outstanding frames, and if the error is detected, then the destination has to reply with what we call rejection. Reject, R-E-J. It discards that frame and all future frames until error frame is being received correctly. The transmitter must also go back and retransmit that frame and all subsequent frames. So once there's error, we discard all frames and all future frames that were transmitted or will be transmitted. Now we want to look at the first case of the go back and ACK, which is the damaged frame. Once a frame is damaged, so we will use station A and station B. So station A transmits the frame X, then station B sends a reject X, which is indicating that the frame has been damaged. Now when A receives the reject, it must retransmit frame X and every other subsequent frame that was transmitted. The second case is that frame X gets lost in transmission. Now, the transmitter has to send X plus 1. This is just to tell the receiver that now the frame you sent got lost. So I didn't receive frame X. Okay, so the receiver gets frame X plus 1 out of the sequence. Then the receiver has to reject X. Then the transmitter goes back to frame X and retransmits that. That is the second scenario. Now, with the third scenario, frame X gets lost, but no additional frame is being sent. So the receiver gets nothing and returns neither acknowledgement nor reject. Now here, the transmitter will just time out and send an acknowledgement frame with what is called the P bit. This P bit is set to 1. Now, when the receiver receives this, the receiver interprets this as a command which it acknowledges with the number of the next frame it is expecting. So the transmitter then retransmits frame X, which gives us the third case. Now, we looked at the damage frame. What about if the damage acknowledged, or if the acknowledgement is damaged? So we have damage RR. We said that RR is receive ready. What about if the receive ready is also damaged? So the first case is that receiver gets the frame I and then sends the receive ready, which is I plus 1. Now if this I plus 1 gets lost in transmission, acknowledgements are accumulated. So the next acknowledgement will be I plus N, and this may arrive before the transmitter times out on frame I. Now if the transmitter times out, it sends an RR with the P bit. Remember we set the P bit to 1. So it does the same thing. Once there's a timeout, it will send the RR with a P bit. And this can be repeated a number of times before a reset procedure is initiated. Then we have the final type of ACK, which is a selective reject. Now the only frames retransmitted are those that receive a negative acknowledgement. Once they don't receive a negative acknowledgement, they don't get to be retransmitted. You remember in the stop and wait, when one frame gets lost or gets damaged, every other subsequent frame will need to be retransmitted. But in the selective reject, we only reject frames that have negative acknowledgements. Subsequent frames are accepted by the receiver and are buffered or are kept in the storage. This minimizes retransmission, and the receiver must maintain a large enough buffer to be able to contain those subsequent frames that were accepted. Of course, it's expected that there's a more complex logic that will be implemented in this kind of transmitters.